Hello, standoff. Next report to be delivered by Slava Moskvin is entitled, "In a very grandiose manner, I'll teach you to hack factories." So let's watch it, enjoy it, don't forget to like it. Thank you very much. I'm extremely grateful to all of you guys, all those who are interested. We've actually been preparing this report since the very beginning of the year. And though we haven't been able to do everything we planned because of the pandemic, but I do hope you're going to enjoy what we have been able to achieve. I guess many people present here today have been exposed to this to this task of hacking a factory, or say a particular ACS system or a SCADA system, regardless of which side of the barricade you're on. A classical pen testing situation is such that you need to hack a factory real quick, but there shouldn't be any human casualties, because if you blow the factory up, your customer will not be happy. So for the next 3 days, we'll be discussing this particular subject: hacking a factory and defending against such hacks. If we have people in the audience responsible for running factories like this, well, you will be particularly interested, because we will be talking here about real-life scenarios. I am very open to any questions you may have, and I'll try to answer them. If we have extra time left, on day 3, we shall have a Q&A session. Let's get going. So how does a modern factory work? Actually, I'm saying a factory, but it actually applies to large ships, power plants, and other industrial assets. Most of them are managed by industrial automated control systems. So it is not automatic, but it is automated. It means it is helping humans, but all decisions are made by humans. Now, we are calling it an industrial system because, well, there is some process engineering involved. For an electric power plant, that would be generation of electricity. Let's consider now what it looks like on the inside. This is a complicated schematic, and usually, because it's complicated, we break it down into several layers. Please note, however, that this breakup, so to speak, is very notional. It's highly subjective. You should not be surprised to see that in real life, different levels will be called different things. Let's start with the field level. At least that's what I call it in my schematic. And I suggest we start with these components. These are actually the units that perform the work, quote unquote. I'm referring to motors and switches, regulators, drives, you name it. But also, there are lots of gauges and sensors that work in real time, generating data streams or the operation, or if you like, performance of the operational assets. Next level is the level of control. And we have controllers over here and here. Why do we have so many of this, and what is it that they do? A controller is an industrial box, an industrial computer, designed to perform a single function. So it is sort of simple, but it's in fact not, because it has to be very good at performing this single function. So usually controllers are running on a bunch of algorithms developed by process engineers, and they process data coming from the sensors below. And in line with this data and the onboard processing, they will regulate valves and other fittings and equipment. All this could actually exist just like that on its own. However, we also have humans who really want to stay on top of the things. So we have workstations and servers connected to them over here. Sitting behind these workstations are operators, usually a bunch of them, and they will be monitoring closely key performance indicators. Some of them have the luxury of managing their equipment remotely from their workstations. Not so lucky ones actually have to do the legwork and reach the individual units that they want to manipulate. And at that level, we have, say, fleet managers who actually don't care that much about individual units, but they've got their higher level KPIs they really care about, such as overall energy usage. And then this data may be aggregated and may be sent onto the dashboard of some top manager. Well, because this particular ship or this particular power plant may belong to a big holding company that wants, to properly manage their assets in a holistic manner. Let's look now at PLCs. I've said already that controllers, or PLCs, are industrial single-purpose computers. They were designed to be used in plants, and they were designed to be pretty robust. Many of them sit pretty close to the gemba, so to speak. Many of them are vibration resistant. In terms of their temperature-wise operating ranges, they are much more versatile than your regular computers. So PLCs can be modular or otherwise, but that's something we're probably going to explore later. Suffice it to say now that PLCs are actually managing the equipment on site. And PLCs receive the outputs of all the sensors. Now let's discuss operators. What you see in the slide now is a mnemonic diagram. This is what operators usually keep hours staring at. It is showing schematically all the key units of equipment that an operator is responsible for monitoring. And next to them, they can actually see readings of critical indicators. A given operator may be looking at one diagram like this or a bunch of such diagrams. The density, the number of such diagrams that a single operator needs to look at will depend on the complexity of the process. Usually, operators will be sitting in what they call a control room. And on average, this will be a group of 5 to 10 people. They are surrounded with a bunch of monitors. Now that you have been briefed on this subject, let me tell you what needs to be done if you really need to hack a factory. Now, confidentiality, availability, and integrity is the classical security triad. However, it doesn't work that way in blunts. Like, confidentiality is not a concern really for blunts. However, integrity and continuity of the technological or operational process itself is of paramount importance. Well, because if something happens to it, there will be financial losses and potentially there may be loss of equipment. So this is a risk that most customers will primarily care about. However, in order to actually endanger this, you need to get control of the equipment, which is usually the objective of the perpetrators. This is it for the introduction, which means that now we can turn to analyzing the individual nodes or individual elements of an automated control system. If you have any questions regarding this introduction, now is a great time to ask them. Okay, let's consider the structure of such a system. Usually, if you have a blunt, that needs to be InfoSec tested or pen tested, it may happen that you actually break into the corporate network of the blunt, but then you actually need to break into the automated control system network, which will be a different one. So if you are on the corporate network, you may actually face what's called an air gap. Actually, many companies claim that for reasons of security, they've installed an air gap between their industrial network and their corporate network. In reality, this is not true. 95% of plants no longer have it or have never had it. And there's a very simple explanation for that. In the modern world, people really need to have access to timely information. It's not just the operators, but it's also the shift managers and the plant manager, and also, say, a division head. And these guys are not connected to the industrial network. They are connected to the corporate network alone, which means that they hate the air gap. Moreover, regulators very often care about information like this, which means that the plant has to report on a number of indicators on a regular basis. And as long as you have the air gap, transmitting this information becomes an arduous activity in its own way. That's why most companies no longer have the air gap. Well, next, I would expect to find a gateway leading to the industrial network. This gateway can come in a number of guises. Some companies actually don't have it at all. In most cases, it does exist. There will be, say, a firewall, or there will be a different VLAN, or it could be an OPC server. An OPC server will take information from the industrial network and will transmit it to the corporate network. We'll discuss OPC servers later. So behind this gateway, which needs to be hacked usually, in order for you to end up in the industrial network, you will usually find the following range of industrial equipment. There will be operator workstations, and we have reviewed them briefly already. So operators, for example, will monitor and manipulate a particular technological process. Also, there will be engineer workstations. And engineers, obviously, are the people who will, for example, reconfigure the software running on PLCs. And they may also fine-tune the software being used by operators. We may also find other servers there as well. It will really depend on a particular deployment and a particular type of automated control systems. Also, quite naturally, we have PLCs connected to individual equipment units and feeding information they collect from the sensors to operator workstations. Also, you can find the so-called protocol converters. So obviously, a converter accepts one type of protocol and emits another type of protocol. They may be required if you're using some legacy devices, or, for example, if you have, say, RS protocol, which is not really a network protocol, right? To something that is Ethernet transmittable. Actually, all or pretty much most units on an industrial network will talk to the PLC. Modern PLCs support pretty much everything happening in a plant. Modern PLCs will support networking. However, there are some outliers. So, say, PLCs may be connected, say, to the workstations or servers directly, not over the Ethernet. And also PLCs may be connected not via twisted pair, but say in a daisy chain, in a loop. Also, PLCs will be controlled and managed using the so-called industrial protocols. They may matter for information transmission, but also some of these protocols are used to manage the PLCs themselves. And this is something that we are going to consider or maybe discuss in more detail today. Actually, I do have a longer talk on PLCs scheduled for later. Let's start with the simplest system possible. Let's look at the workstations of the operators. Oh, I'm sorry, I see a question in the chat. Unfortunately, the question wasn't really audible. So many people talk about it, but I have never really seen those gadgets in place, in the wild, so to speak. Oh, right, so this is information diodes. I've heard of information diodes organized via VPN, and it was considered one of the most secure arrangements. Such workstations, are needed in order to display information about the process itself. And this is what they look like in most cases. Okay, so in SCADA systems, we very often have operators able to manage the equipment remotely. And usually they use so-called safe commands to do that. They're called safe because it's either in the software of the SCADA system that there may be a limitation on, the range of of variables they can operate in, or other constraints may be imposed. Why is this important? At any point in time, the PLC will be monitoring the variables of the technical process, applying the so-called protection and blockage logic, which means that it is engineered in a way to assure that no harm is done to the equipment. And this logic can be maintained in a single PLC, or alternatively, it can be done at the stack level on the main PLC. In certain assets, such as nuclear power plants, you will see the so-called 2 out of 3 system, where you have 3 PLCs, and before anything is done, they need to negotiate if data coming from 2 PLCs is the same. Then the action is vetted. The action is given a green light. So this is another layer of, redundancy, you may argue, but it's also a layer of protection. The information displayed and the number of workstations used will depend directly on the complexity of the process. So obviously, the more complex the process is, the more operators will be required. Like I said, these workstations are usually kept or usually used in the so-called control rooms. So let's approach the first practical session, but before we do that, let's refresh again the things you can do with operator workstations. If you have been able to hack an operator workstation using, say, some common vulnerabilities you discovered using the pen test, first thing you can do is actually look for documentation on this workstation that you will require to better understand what's happening in the asset. Maybe you will discover a list of passwords, or you will learn about risks that the client is particularly concerned about. This information should enable you to mount the next stage of your attack. If you have hacked a workstation of an operator, you should have access to the PLC, because PLCs talk to the workstations. And you do need access to PLCs in order to trigger risks that have the highest criticality levels. And you will obviously be able to do things that an operator does. After you've gone through authentication in the SCADA system, you can manage the process an operator would do. Well, given the logic of PLCs, you will be restricted to safe operations primarily. So you won't be able to blow the factory up. However, you should be able to impact the process negatively. Now we shall have a demo time. This demo will involve our booth, I think our mock-up, and the SCADA system we have developed for this mock-up in particular. So, guys, we'll need to switch the camera now for demo purposes. Oh, so it's not a mock-up, it's indeed a booth. So on this bench, what you can see is that we are actually pumping some air into the balloon. So here you see valves that regulate that regulate the airflow. There is also a pressure sensor here. All this stuff is connected to the PLC using this hose of wires, or cables rather. And the valves are also connected here to the output modules, which means that the PLC will collect information from the pressure sensor, and based on this information, it will decide how to use these valves. Let me show our SCADA system to you now. This SCADA system is certainly a toy compared to real-life systems, but this is what's good about it. And this is what we used last year in the Industrial Ninja competition. And we're going to use it now in order to emulate different attacks for your pleasure and entertainment. So you can see here the balloon itself, its current pressure, and the three valves. There is an inlet valve, there is a discharge valve, and there is an emergency valve, which is actually this red button I have here. So let's assume you already have access to SCADA. You can already do things. And I'm considering, and I will be showing it based on the assumption that you are a malevolent operator. You see this toggle? It's called manual mode. Let's put in the manual mode's password. In real life, in a real asset, you won't really see a toggle like this, but we need it for demonstration purposes. Now I'm guessing the command did not go through. I'm sorry. It's not ideal yet, but it does happen so often, particularly in demonstrations. So please bear with me while I do it the second time. So you can see that the system now is in manual mode, and we now see the icons for manual operation. So I can, for example, switch this valve on. That will require that I go through authorization as an engineer. And then the PLC will no longer apply logic, and my balloon will continue to inflate incessantly. So you see that the balloon is inflating. And if I press the button, nothing happens. And the only way I can stop the process is by switching the PLC off. Obviously, this is a situation to avoid. Now, had I not shut the PLC off, the balloon would pop. And since it's an emulation of what can happen in a real site, that would mean like an industrial explosion. Okay, let's look now at an engineer's workstation. Engineer's workstation is usually a juicier target than that of an operator. The reason being that, although it all depends on the architecture of a particular asset, but quite often engineers will have direct access to PLCs. Moreover, these workstations usually have the software installed for managing PLCs. In just a couple of minutes, we're going to see what you can do to such workstations. Actually, the range of things is quite impressive. Actually, some of these workstations are fixed, but not necessarily so. If it's a laptop, chances are you will be able to connect to other devices as well. So what can you do to an engineer workstation if you have hacked into it? You should be able to make changes to the SCADA project. You can, for example, mislead the personnel by messing up with the mnemonic diagrams. You can also change the variable bindings, again to mislead the personnel. For example, an operator may be thinking that everything is fine in the plant, while you are having fun with the equipment. If the engineering station is connected to a PLC network, you should be able to abuse the engineering software to rewrite the variables. You should also be able to reinstall the firmware and, for example, install some malicious firmware. And other horrible things, I guess, can also be perpetrated. Just like with the, compare it to an operator's workstation. You have more room for maneuver here. So let's turn to our second demo now. So we have the engineering software running on my virtual machine here, and we will be using a PLC from Siemens called SN300. It is actually a very well-known piece of equipment with long history. I don't think that any new units will be using it. This is actually a highly prevalent device in the market. So chances are, if you are into this sort of thing, you will run into SIMATIC 300s quite often. So let's look at the engineering software involved. So with the help of this software, I will connect to the PLC now. If I press this button, I will go into what they call online mode. This term is sort of specific for this software. And it means that while I'm connected to the PLC, changes will be made to the PLC directly. And we are connected now. So I can actually press the right-hand mouse button and choose Display Force Values, which I think is a great opportunity for me to discuss what variable forcing is. PLC software, just like any other piece of software, will manipulate a number of variables. We'll write them down, change them, and so on. You can use engineering software to force certain values onto these PLC variables. This is what's called forcing. And you can use the forcing function in order to rewrite or write on top of any information on the PLC. And this is how you can exercise significant level of control over the equipment. Let me restart our bench again. I will use my engineering software now to enter the address of the variable I want to change. It's called Q00, which means that this is like the first output. And you see that the address starts with zeros. However, if I enter true here, it means that it should turn on. So you will see me pressing the right-hand button and choosing force, then pressing yes. And what you see here is that the balloon is being inflated now. Here in the output panel, we can see that all the outputs are now on. Also, I can prohibit the air from escaping the balloon. And again, choose force here. So as you can see, the balloon continues to inflate sort of uncontrollably. If we don't stop that, it is going to lead to pretty disastrous results, at least for the balloon. See, you need to lower the volume because I'm about to explode this balloon. Congratulations, we've popped it. Great success. So we've blown up the factory. Men are screaming, women are crying, you've been victorious as a bad guy. Let me showcase some other capabilities of this engineering software now. Besides all these scary bits, you can use the engineering software in order to manage the equipment in full. For example, I can, reconfigure the software. I can, for example, delete certain modules, or I can change the IP address here of a particular PLC. Certain operators, because of that, will not be able to see the readings collected by this PLC. So the PLC will continue to exist, but it will not feed the information it is expected to feed into the system. I can also use the PLC to cancel a particular production program, which is also a pretty powerful way of attacking the system. Let's look at another interesting opportunity here. Industrial software will run PLCs using a bunch of industrial protocols. Quite often, such industrial protocols are proprietary, which means that their structure is not publicly explained anywhere. However, reverse engineering and a bunch of other tools can solve this problem. So if this protocol enables you to manage or run the PLC, this obviously gives you an opportunity to do all sorts of interesting things. For example, our PLC is using the S7 protocol. There is a particular utility and a library for this protocol called Snap7. It actually enables you to connect to the PLC via this protocol and manipulate it. It is actually a pretty multifunctional utility. Actually, it is quite comparable to full-fledged engineering software in terms of its functionality. So you can see that I can use Snap7 in order to connect to a PLC. And here in the Control tab, I should be able to manage it to run. See, it was running now. I can stop it now. And this obviously means that the program running on the PLC will stop. The PLC will cease to manage its outputs, will cease to obtain information from the sensors, which means that everything we had there will sort of freeze in the state right prior to the stop. And this will rid the operators of the opportunity to manage the technical process. What's funny about these utilities is that you don't actually need to have the engineering software to manipulate the PLC. Actually, engineering software tends to be bulky, sometimes it's difficult to obtain, but this is a lightweight utility. It weighs just a couple of megabytes. And it gives you access to the controller. Certain controllers are equipped with some protection against it. For example, you will need to enter some passwords and stuff. However, these defenses tend to be haphazard. In most cases, they are not found. And even if it is supported on the hardware level, there is no guarantee that a particular company will use it. Well, because usually they don't care about cybersecurity that much. They care about operational convenience and performance. Let's turn the page on engineering software. And I am nearly running out of time for this session. So let me tell you very briefly about PLCs. And we shall keep the server discussion until tomorrow. From the viewpoint of a hacker, PLCs may seem like a black box. A black box with some network ports open. You may have a difficulty detecting vulnerabilities on a PLC. But don't get disappointed yet. If you have a team and if you have a bit of time, there are things you can do with a PLC. Shown in the slide here is a case from one of our real projects. We had a PLC which had several network ports open. So we had a web interface running. There was also an RPC bind service for the operating system, and obviously the operating system used was VxWorks. Also, it was running several program modules supporting certain protocols such as 104, which is electricity protocol. Another one was for OPC UA module. And also it had several ports open for the proprietary industrial protocol, which gave you pretty much full control of the PLC. A profound analysis led us to realize that you can use the web interface to actually read and write any variables, which means you can already impact the processes. You can use port 111 to mount a DOS attack, which is also a bitch if this is an important PLC managing some important process. 2404 could be used for RCE, 4840 for another denial of service attack, but most importantly, 69 and 59 ports designed for the proprietary industrial protocols. We were able to do whatever we pleased. RCE, DOS, arbitrary memory read-write, PLC control, program modification, variable forcing. I have just shown variable forcing to you, haven't I? And we were able to do the same with the second port, which only shows how poorly protected our industrial devices may be. Let me give you a short preview of what is coming next, and this next will actually happen tomorrow. Tomorrow, we shall discuss gateways in detail, the gateways that separate the industrial network from the corporate network. And we'll talk about hacking the gateway, about using the features of the software running on the gateway. And after that, we'll drill even deeper. I think this should be it. I think the time is nearly up, so I can take a question or two. And if you have any questions outstanding, please submit them in the chat, and I'll try to take them. Okay, people are saying they were not able to copy the links from the slides. We are going to make the slide deck available in any case, so that you can study them at your leisure if you're interested. Let's wait just a bit in case there are any questions coming through. That's a great report. Thank you very much, Vyacheslav. Let's wait just a bit, hoping there will be questions. In your opinion, are you able to hack most plants today? Or in other words, how often do you run into configuration issues that enable you to perform your pen test quickly? Well, every time. You know, if you spend enough time, you will discover either critical vulnerabilities or misconfigurations, enabling pen testers to do as they please. Well, obviously, we are there to help them find those vulns and defend better. So obviously, we tell the vendors and we tell the customers about all the issues we've uncovered. Sometimes it's just a matter of patching your system. Great, thank you. Okay, question one. Have you been able to get access to Shadow Xworks? Yeah. This was not done on the latest equipment, but there was a real PLC that had a shell with comments open, which gave us access to Xworks. So we could use Telnet or some such to get access to the operating system. For example, we could easily do arbitrary RAM read-writes, which is not good. I don't think it's possible in modern equipment, but that was quite some time ago. So you said that air gaps are missing in most cases. Did you have cases where you had to hack the system where an air gap existed? I don't really remember cases like this. There possibly was one case like this, but back then we were not asked to hack the system, we were asked to order the configuration. So I'm guessing that had we been summoned, to actually hack it, we would have discovered there was no real air gap. Where do we find research on controllers? Well, there are places for that. There is no central repo, but use your Google. Actually, PLCs are quite different. If, say, a PLC supports some open standard protocol. Individual vendors will build in some proprietary features into them. So people will often reverse engineer them, write their own scripts, and upload them on GitHub. This should be it for the questions. I'm certain there will be more. So Vyacheslav can spend some time here taking these questions, but in the meanwhile, we will prepare for the next presentation, starting in roughly 5 minutes. And it will cover, surprise, surprise, advertising. 2 stunning ladies are going to tell us about the horrible dangers of the advertising business. So please stay tuned.